If we said deep water wave, then you obviously imagine there must also be a shallow water wave, right? So the depth of the ocean varies. So we said open ocean, wind-driven waves mostly tend to be deep water waves because the depth of the water column is much greater than the wave base, which is half the wavelength in this idealized waveform. And obviously, if the depth decreases to some level, some depth decreases to some depth, then it becomes a shallow wave, shallow water wave, because the wave begins to feel the bottom. Where does it happen? Basically, when the water depth is less than 1/20th of the wavelength, 1/20th of the wavelength, then the wave becomes a shallow water wave. And the most important thing to remember here is that the speed of the shallow water wave then depends on the square root of the depth of the water column. Okay, this is a cute thing to remember, because we'll see how you can use this to impress grandma again when you go to the beach. So the celerity, we write it as C for celerity in meters per second, is 3.13 times square root d in meters. So 3.13 is basically the square root of g, the acceleration due to gravity. So the wave speed is basically square root g d. D is the depth of the water column, or in feet per second is 5.67 times square root d. And you can see here that the as you get close to the coast, the waveform begins to deform. It's not a pure circle anymore. It becomes elliptic, and in fact it begins to tilt over as it approaches the bottom. And you can do this experiment very easily, actually. Next time you go to the beach, you stand in a let's say water up to your knees or hips or whatever, and you feel the waveform. You can feel the sand making a circle around your feet, basically because the waves are coming in, they are flattening, and they are basically making a circular motion or an elliptical motion at the bottom. That's what this figure is trying to show. Okay, so the wave at the surface is not a pure circle anymore, it's elliptic, and then as you go deeper it tilts over and becomes horizontal. Okay, so the deep water wave was wavelength over 2, depth greater than wavelength over 2. Shallow water wave is when the depth becomes less than 1/20th of the wavelength. And in between you have these so-called transitional waves, which have both the deep water kind of characteristics and a shallow water wave characteristics. Okay, so the celerity depends both on the water depth and the wavelength. We have to go through the theoretical calculations to do that. We won't do that here, but you can see that the waveform is more circular. It is getting squished as you go down. It is getting tilted, but doesn't necessarily hit the bottom unless you reach this 1/20th of the wavelength. So you are essentially transitioning from a pure deep water wave where the wave doesn't feel the bottom to where the wave is partially feeling the bottom, and then ultimately it completely feels the bottom and the waveform hits the bottom. So those are the transitional waves. What are the kinds of waves that are generated by the winds then? Okay, those are deep water waves, transitional waves, and shallow water waves. But is that all there is? Actually, as the wind begins to blow over the ocean, imagine that it's a very calm day. Wind begins to pick up. Initially, the waveforms will be just very light ripples, right? And wind stress, when it's very light, it generates what are called capillary waves. Where does the name come from? As I said before, the name typically corresponds to the restoring force. So wind is the perturbation force that is generating the waves, and the waves happen because there is a restoring force called capillarity, which is basically the surface tension. Remember that water has this special property of dipolar structure, bent shape, positive negative towards the oxygen and positive towards the hydrogen. So each molecule combines with another molecule to satisfy polarity. and we get hydrogen bonds. When we said hydrogen bonds are strong and you cannot easily break them, we saw Jesus lizard walking on water, many insects walk on water, and so on. So capillary waves use this surface tension as the restoring force, okay? Or the capillary waves are created when the winds are light enough and doesn't break the surface tension, you just get these ripple. The word capillaris actually comes from a Greek word for hair, so the waves feel like hair. So if you imagine yourself floating with your head down in a bathtub or water, and the hair will make, well, not me, I don't have any hair, but if you have hair, it forms these kind of ripples. That's where the capillarity or capillaris comes from. Okay, gravity waves. As the winds get stronger, the surface roughness increases, and the wind is able to grab the surface by friction because of this roughness, and the wave length and wave height begin to increase. And at that point, they're called gravity waves because gravity is the restoring force, right? So here it is as a schematic. Light winds, you have a typical wavelength of about 1.74 centimeters, very idealized. Capillary waves just form ripples. Wind generates initial stress on the surface, these capillary waves. As the waves get stronger, you get wavelengths of order 10 meter, and gravity, as the wave height increases, gravity pulls it down, wind pulls it up, gravity pulls it down, so we call that gravity waves, and they have more energy transferred from the wind into the ocean. Wave height squared corresponds to the wind wave energy, and they have these what are called trochoidal forms, so this kind of conical shape. And obviously as the winds get stronger or as the waves approach the coast, if the steepness becomes greater than 1/7, height becomes greater than 1/7 of the wavelength, then the wave breaks because the trochoidal form becomes so steep that gravity begins to just break the wave form and pulls the water down. Okay. The main concept for sailors then is the so-called sea. Out in the open ocean, you have, as I said before, at the beach you may not feel any wind and you may still see waves coming in, maybe sometimes pretty strong waves, and breaking at the beach and creating a lot of surf. Okay, if you go to any beach next time, you can watch this carefully. Why is that? Because there is a storm out in the open ocean which is called the sea, which is churning the ocean and creating waves. Okay, that area where the storm is brewing the ocean and churning the ocean is called the sea. So the sea produces different waves, different wavelengths, and the waves get sorted out, and what comes at the beach depends on how far the sea is and how strong the storm is and so on, and what amount of energy is coming in, what the topography of the beach looks like, and so on. So we'll see the details in the next podcast. So just remember, transitional waves, shallow water waves, capillary waves, gravity waves, the sea where the ocean is being churned by the winds.